concept statical determinacy of structure. Statical determinant. We use the word statical because we are going to use the statical equations like sigma of x equal to 0, sigma fy equal to 0, and sigma m. If the number of unknown unknowns in your structure is equal to the number of equations, then it means that you are able to find unknowns. Because, for example, you have 3 unknowns, you have 3 equilibrium equations, then using a system of equations, you are able to find the unknown. The number of equations when it comes to 2-dimensional view of your structure is 3. So those equations are, as you know from statics, sigma fx, sigma fy, and sigma m. So this number is fixed. It is always 3. So we can say that if the number of unknowns in your structure is equal to 3, then your structure is determinate because you are able to find all the unknowns. We will solve a lot of problems for this. So now we go for statical indeterminate structures. So in this case, the number of unknowns is more than the number of equations. Again, the number of equations is 3 when we talk about 2-dimensional view structure. So this is the definition of determinate and indeterminate structure. But some of the structures are very complicated, so we need to formulate this, and we use the formula. The textbook is using a formula which is not generally used for all of the structures, so I'm going to propose a formula here that is applicable to many of the structures. So from now, we use that formula. But just want to put emphasis on this. If the number of unknowns is greater than the number of equations, which is 3, then the difference between these two numbers is the degree of indeterminacy. It means that if you have, for example, 5 unknowns, and you always have 3 equations, then you have 2 extra unknowns. So 2 is the degree of indeterminacy of your structure. So the difference between these 2 is called degree of indeterminacy. And then we show it with di. So now, most of the questions are looking for this value, how to find degree of indeterminacy of a structure. Any question? Yes.
Is it related to degrees of freedom in other fields?
It is confused with degree of freedom, but they are different.
Okay.
Yeah. So you learned a little about degree of freedom in the first chapter of statics, but it can be related to degree of freedom, but essentially it is different. So you just follow this formula, and then I prove this formula for you so you understand how we've derived this formula. So now, we are going to discuss this concept for beams and 2-dimensional frames. Beams and 2-dimensional frames. How to find the degree of indeterminacy for these structures. This is the formula. Degree of indeterminacy is the number of unknown minus the number of knowns or equations, right? There are some conditional equations adding to number of 3. So it means we may have more than 3 equations in addition to these 3 fixed equations, sigma of x, sigma of y, and sigma m. So we will see how. I write here the number of known minus, this is unknown, unknown minus known. In general, r plus 3k minus c plus 3. 3 is the number of equations that we always have. 1, 2, 3. We always have these 3 equations. So this number is fixed, 3. C is the number of conditional equations or number of condition equations that comes from the internal hinge or pin. So now I introduce these parameters here. R is the number of support reactions, which is unknown. Number of support reactions. It depends if you have a fixed support, if you have a pin support, etc. K is the number of rings. I know you are not familiar with rings, we will discuss it. Or some people call it closed loop. And C is the number of condition equations. Okay, so don't worry about these parameters because we are going to discuss all of them. So there is a question here and then we discuss these parameters with that question. Consider there are 3 rings intersecting each other. This is a closed loop. Imagine this is made of steel bar and just in this shape. It is welded to another loop and it is welded to another loop. And then they are sitting on a pin support. And here another pin support. We are going to analyze this structure based on that formula. And then we will look into the proof of that formula because you need to know what's the proof of that. So the question is asking to find the degree of indeterminacy for this structure. Look at the first parameter, number of support reactions, which is unknown. Okay, we have a support reaction here, which is pin. How many unknown reactions we have for this? Okay, look at here, the reaction horizontally.
About 2 then.
Yes, and the reaction vertically. So do you agree when it comes to pin support, we always have 2 unknowns? Because it's a pin support. So I put 2 here. If it was a roller support, then how many unknowns we had? 1, yes, because it's a roller support, so the unknown is vertical. If it was a fixed support, how many unknown? 3. Yeah,
Oh,
because
okay,
because it has moment as well. So you learned it in, I'm sure you know it, you learned it in statics. Okay, so roller support always 1 reaction is unknown, pin support always 2 reactions, fixed support always 3 reactions. The other support is also a pin support, so we have 2 unknowns. two reactions that are unknown. When it comes to the closed loop or ring, wherever you cut your ring, just cut it. You have a reaction in this direction. You have a reaction in this direction. So this is normal reaction, this is shear reaction, and you have a moment. You learned it in statics. Normal, shear, we showed with V, and moment. We always have three unknowns when you cut part of an element. It doesn't matter, it is part of the ring or part of the beam or column, etc. You have three unknowns. Remember, three unknowns for a two-dimensional view. When you have six-dimensional, when we have x, y, z for three-dimensional view, then the number of unknowns is 6. But we just cover two-dimensional view. So do you agree that for each ring, we have three unknowns for each ring? Doesn't matter, this one, this one, this one. So K is the number of rings or closed loop. And because for each loop or ring, we have three unknowns, then 3 times K is the number of unknowns. So I have one loop here, I have another loop here, so we have, for each loop, we have 3 unknowns. This is how we derive this equation. The number of rings times 3, because each ring has 3 unknowns. So if you have 10 rings, then you have 30 unknowns. So this is the proof. I'm just proving this equation for you. Support reactions are unknown. We have 3 unknowns for each ring. We add them together. The first parenthesis is the number of unknowns. Any question? We just proved it. And then we need to subtract the number of known equations. So the number of equations is 3. As usual, you know sigma fx, sigma fy, sigma m. But sometimes we have some conditional extra equations because of internal hinge that we will discuss in next problem. So in this question, we don't have any internal pin. So C is 0. Okay, so far R in total is 2 plus 2 is 4. Another thing is how many closed loop we have. You need to be skillful if you want to identify the number of closed loop. Now I'll show you. This is 1. The second one. The third one. 4. 1, 2, 3, 4, 5. So the number of rings or closed loop is 5. When we say ring, it may confuse you. It's better to say closed loop. So this is 1 closed loop, second, third, fourth, fifth. So K is 5. And because we don't have internal pin, the number of condition equation is 0. We will discuss it in next problem. That's it. So you just substitute them into this equation. Di is R, which is 4 plus 3 times K minus C, which is 0 plus 3. What's the answer? 16. Yes. This structure is indeterminate by 16 degree. It means in addition to number of equations, that is 3, we have 16 unknown. So we cannot solve this, we cannot analyze this structure using the equations given in statics course. All of the problems you solve in the course statics were determinate. That's why you always use these 3 equations and you were successful. But if the number of unknowns are more, then you need some extra equations. In this course, we try to derive some of those extra equations. For example, one of them is slope deflection, is one of the chapters we discussed. We will go through them. So now we are just going to identify the degree of indeterminacy. And this is a good topic this is a topic of interest for FE exam. We always have one problem from degree of indeterminacy. If you look at the textbook gives another formula which is less general than this. So it is not applicable for some of the complicated structures. So I assure you, you can always use this formula for beam and two-dimensional frame, and it is successful. And then I just proved it for you. Okay, so this was one example. We keep solving problems for this formula for today. Any question? Yes?
So the C is 0 because nothing's happening to it?
C is the number of condition equations. It depends on the number of internal hinges. Because we don't have hinge in this structure, it is 0. But in next problem, I will cover it.
Okay.
Yes. So I'm going to erase the top part. Right? And you have most of this information in PowerPoint slides or PDF files. So, but it's good to take a note in the class, but don't worry about, most of them are available on the PDF file in Brightspace. So before we solve some of the problems, we need to answer her question. She's asking about C. So basically C is about the connections. So we are going to look into important connections which you have seen before in statics. I'm sure you know about this internal hinge. So this is part of the structure. We have internal pin or hinge. When it comes to this pin connection or pin joint or pin hinge, you know that there is always one equation, and that one is moment is 0. You know this, right? So this is called condition equation, the one that she asked. So how many condition equations we have here?
2 or 1.
One. Because this is one equation, right? That's it. So now we have a couple of more connections which you may not have seen before. Shear hinge. Some of the textbooks include this. We call it shear hinge. Usually professors don't discuss it much in the class. They just give a clue about it. Here, if you grab one side of the structure, the other side can easily rotate. That's why moment is 0. Here, if you grab one side of structure, the other side can easily vertically move upward and downward, like a rail, right? So in this case, something is 0, but that is not the moment. What is 0 here? Yeah, something Fy, but we call it shear force, right? So V is 0. So when you say Fy, it means shear force. When you say Fx, it means normal force. So remember these three. Your Fx is N, your Fy is V or shear force, normal force, shear force, moment. So shear force is 0. So again, this is the condition equation here. So how many condition equations we have here? 1. It is good to think about, can we say moment is 0 if I hold one side of the structure? Can I rotate another side? No, it's not possible. There is a resistance because of this connection. I cannot rotate it. But here, I can easily rotate it. When there is no resistance, it means that parameter is 0. Here, I can easily move it upward and downward. There is no resistance, so shear force is 0. Can I hold one side and pull another side horizontally? No. So we cannot say n is 0. We cannot. So we have only one conditional equation here. This was just a reminder, and we don't go more than these two usually. And in FE exam, I haven't seen this. So if you know this is good enough. So now you know about the connections. We are going to answer her question, how to find C, because you need to solve many questions. We are going to generate a formula for C. We say we have one condition equations here. How many elements or members are connected to this pin? 2. So if I show the number of elements with n and I show the number of condition equation with C, then I can formulate it in this way. Do you agree? 2 minus 1. So you just need to count the number of elements connected to the pin and then subtract it by 1. This is how you find number of condition equation. So now, look at here. We have internal hinge. This is part of the structure, but I'm looking for C. C is n minus 1. We have 3 members connected to this, so it's 2. But try to understand what we are doing. I know you can just use formula, of course, in the exam, in FA exam, you can use formula. But basically here I said I hold one of the elements. For another element, I have one equation. So here I can say the same. I hold one of the elements and I cut it here. So I have m equal to 0 for this part. I cut it here as well. I have m equal to 0 for this part as well. So for each of the elements, I can have one equation, regardless of the first element, which is the reference. So this is the proof. Some of the students don't like the proof, they just follow this equation, which is fine, but it's better to understand what you are doing. So now if I increase the number of elements connected to this pin, then it means I'm increasing n. Next example is this one. We have a pin support and 3 elements are connected. How much is C? The same formula. How many elements are connected to the pin? 3, yes? So the answer is 2. Right? This is how we find the number of condition equation. Look at this. We have element like this. How much is n here?
2.
Yes. Not 3. Is there any question why not 3? Because the pin is not inside this element. So this is one member. This is another member. We have 2 members. Be careful about these details. If the pin is inside, then we have 3 elements, right? So be careful about it. C is n minus 1, n is 2. So number of condition equation is 1. Next example, we have a pin support. And these are the elements connected. How many elements? Yes, 5. The number of condition equations is 4. Any questions so far? Okay, next example. We have element What about this? How many elements?
2, 3, 2,
2 or 3?
2.
Okay. This is one element. This is a single element. It means here is welded. But in the textbook, they don't show it. So be careful about the location of pin. And if it is not clear, for example, during the exam, if the print is not clear, you can raise your hand. I will tell everybody if the location of pin, because you must know. So C is n minus 1, which is 2 minus 1, which is 1. So you can see this course is a little tricky compared to statics. It has a lot of details. Details like this. And usually they don't discuss it in the book because the book is already, I don't know, 1,000 pages. They don't want to double it. Next, you have all of this question in the PDF file in Brightspace, but you don't have the solution, so you need to take a note in the class. Now, what about, we have a roller support. Okay, how much is N? This is a roller support, so what? The pin is still pin. It doesn't affect our discord. It is still a pin. We don't care about the roller, right? So if it is a pin roller, if it is a roller support or a pin support, it is still a pin. So 3 minus 1, 2. The difference between roller support and pin support is when it comes to number of reactions, R. But when it comes to C, it's the same. And what else? Okay, I erase this part. What about this? How many elements? Yes, 1. Because basically this part is welded, but they don't show it. So C is n minus 1, 1 minus 1 is 0. It means we don't have a condition equation. Okay. Because this is just one element. So C is 0 in this case. How many elements?
4.
Yes, 4. Because this is a single element. And 1, 2, 3, 4. So C is 4 minus 1, 3. Okay, good enough. So now you're in a good situation to find the number of condition equations. So these are just part of the structure. So this is the answer to her question. Because Alex was asking about how to find C. So these are just part of the structure. I cut them out of the structure. So in a single problem, you see an entire structure which includes all these pins or hinges. And then you need to identify the number of condition equations. So sometimes the support comes inside the structure. The support doesn't necessarily need to come out of the structure. It means part of the structure can sit on another part of structure. So we have internal supports. Internal. Internal support means that the support is not connected to the ground. Not connected to the ground. It is inside the structure. So the way we treat the internal support is that we just replace it with internal pin. That's it, because it is acting like a pin. So look at these examples. This is part of the structure sitting on another part of the structure. So we have this element, we have, so two elements of the structure are connected together. One element is sitting on another by internal support. In this way, you just treat this internal pin support like an internal pin. It means that we can redraw this in this way. There is an internal pin. That's it. And then the number of condition equation is 2 minus 1, which is 1. That's it. Another example. We have two elements. This is the pin. So this is internal support. So it means that we just cut it out of the structure. Part of the structure is sitting on another part. How many elements we have here? Okay. First, to avoid confusion, you need to replace it with a pin. Okay, let's do it. We have one element here, and a single element here. So 3 elements. So number of condition equation is 2. What about so this one somebody will come and solve. Who is the volunteer? We are going to solve a couple of examples. Yes, thank you. So the chalkboard is here. So basically you need to replace it with
the pen, right?
yeah, with internal pin.
This would only be 1, so couldn't we just do
Yes. Yes.
that so then it would just be C equals 2 minus 1, which is
That's correct. And your next problem is thank you. We have an element, we have internal pin. What about this? How many elements are connected?
4.
Yes, 4. And this is internal support. We replace it with internal pin. So C is n minus 1, 4 minus 1 is 3. So if you look at the problems for degree of indeterminacy in the textbook, they are so easy for you now. If you follow this method, you just look at them and solve. The textbook tries to go through the proof for each single problem, which is time consuming. So what you don't need, because you already learned the proof for the general formula. You know each ring has 3 unknowns. And you know R is the number of support reactions. So because you know the proof of the general formula, then of course you can use it for any structure, as long as it is beam or frame. Remember, we don't use it for truss. We have another formula for truss. So now we are just discussing this formula for beam and frame. Okay. Now we go for a roller. The connection which is including a roller. Consider these two pieces of element connecting to each other by a roller. So there are two elements, one of them in yellow, the other one in pink. We are going to find a number of condition equations. How many equations do we have? Can I say moment is 0? If I hold one piece of this, can I rotate the other piece? Yes. Remember, this is spherical object here, acting like a roller. So moment is 0. Can I say normal force is 0? It's a roller, so it's like a train on the rail, the roller. So basically, if I hold one piece of it, I can horizontally move another piece because it is acting like a train on the rail. It's a roller. It's not a pin support. So these two connections are different. This is pin connection. This is roller connection. They are different. So when it comes to pin, we say moment is 0. Only one condition equation. When it comes to roller, we have two condition equations. What about shear force? Can I say shear force is 0? If I hold one piece of it, can I vertically move the other piece upward or downward? No. Okay, so shear force is not 0. So the number of condition equation here is 2. 1, 2. We have two condition equations when it comes to a roller connection. But when it comes to pin connection, only one condition equation. Because this is the only equation that we have. So the way we generate the formula is that here C is n minus 1. But here, the way we generate formula is that C is equal to n. We don't need to subtract 1. Number of elements connected to roller is 2. So C is 2. So basically, you just need to count down the number of elements. You don't need to subtract 1. For pin, you subtract 1. For roller, you don't need. So if, for example, there are 10 elements connected to roller connection, then C is 10. If there are 10 elements connected to a pin, then C is 10 minus 1, which is 9. So now, the same discussion goes for internal roller support. Remember, we have internal pin support. Then we can have internal roller support by just a little change. For example, if I change it in this way, then it is internal roller support. If I change it in this way, then it is internal roller support. So what is the difference? As usual, you can replace it with internal roller, and then the formula is this one for roller. C is equal to N. That's the only difference. So let's look at one problem. The simple problem, for example, we have one element sitting on another element using a roller support. So how much is C? C is equal to, yes, 2. Number of elements is 2, so C is 2. Another question is, how many elements are connected to this internal roller support which can be replaced with internal roller? So we don't subtract 1 because this is internal roller. So number of elements is 3. If you don't understand, this is one element, this is a single element, another single element, another single element. So basically there are 3 elements connected to this roller support, internal roller support, which can be replaced by internal roller connection. So, how much is C here? This is roller. How many elements? 4 elements. So C is equal to N, which is 4. We don't subtract 1. Yeah. So the number of elements is the same. The way you calculate the number of elements is the same. So what about this? This is internal roller support. The number of elements is 2. So C is equal to N is equal to 2. There is a roller support internally. And these 3 elements are welded. They are welded. So how many elements we have? 2. And C is equal to number of elements because this is internal roller. So now you are familiar with number of condition equations. We are just talking about her question, how to find C. You can see a lot of details, usually the textbooks do not separate these concepts. They just give you the entire structure and then you have to identify C and R and K, etc. in an entire structure. But you need to practice number of condition equations separately to be skillful about it. We still have some unusual connections that you may see in different textbooks. We just practice some of them here and try to formulate the number of condition equations for them. So you have all of them on the PDF file. Look at this condition. The first element is like this. Another element, so I try to use different color. So blue elements and green elements are connected together through this pinky color internal connection. By looking at this connection, you must be able to identify about the three internal forces. N, normal force, V, shear force, and M, moment. You always hold one piece of it and then try to move the other piece. Now you tell me, N is 0 or not? Can you horizontally move the blue piece if you hold the green piece? And these are rollers. These are spherical objects. And the green piece is not connected to the end. Basically, it can roll. So there is no resistance horizontally. You can just hold this piece and then horizontally move because these are roller and this piece, the green piece can just slide. So there is no horizontal movement. If I hold the green element, can I move the blue element up and down? No. So there is a resistance vertically, so shear force exists and it's not 0. I hold this element and I try to rotate the blue element. Does it work? No, it doesn't rotate. So there is a resistance against rotation, so moment exists, it's not 0. So the one which is 0 is considered condition equation. It gives us an equation, right? So because of this, we can see the number of condition equation here is 1, and it's because of the first one. So for this special connection, the number of condition equation is 1. There is another form of drawing this connection. These two connections are the same, but different drawing in different textbooks. The same, right? So the answer for both of them is the same. Now, is there any question? I'm moving fast, as usual. This course is a bit different. Yes?
What kind of attachment did you say that was?
There is no name for it.
It doesn't have a specific
No,
okay.
it doesn't have a specific name. These are special connections.
Okay.
We have a pin connection we discussed. We have a roller connection, but we have shear hinge, remember? But for these, there is no specific name. These are just connections. So now I'm going to change this connection and reconsider this. I just put a pin here. Now, what is the difference? N is 0 or not? I'll give you time to think about it.
Yeah.
Yes or no? If you hold one piece and try to horizontally move the other piece, does it work? Can you horizontally move the blue element? Remember, the green element can roll and slide.
Mm-hmm.
So, yes, so N is still 0. What about shear? You hold one element, can you vertically move the other element? Yes or no? You have to imagine this. This is a pin, and the pin is attached to here. So basically this point is attached. Maybe I should draw it in this color. This is attached to this. So this one cannot move up without this. So in this case, you can say shear is not zero.
Shear won't move, but moment.
What about moment?
Moment should be 0.
Yeah, what was your name? I forgot.
Braden?
Oh, Braden. Yes, moment is zero. Yes. Because you can easily rotate it, right? So these are special connections. And I don't expect you to be able to answer the questions, but now you know. So the number of condition equation is 2. Because we have 2 condition equations. Another question is this. We have a shear hinge because Braden is interested in the name. So this is shear hinge. But now if I change it in this way, then there is no name. It's just a connection. So there is a pinky color one and the blue one. Now, what about normal force, shear, moment? Okay, just give an answer. N is 0, yes, but everybody agrees or not? Yes, N is 0. Shear force.
No, N wouldn't be 0, would it?
No.
Wait, is that right?
Yeah, shear force.
N wouldn't be 0.
Yeah.
N's not 0, but shear is 0.
Yeah.
Yes. Yes. Because you can vertically slide it, this one goes up and down, but horizontally you cannot get them away. Yes. What about moment?
That's 0.
Yes, because you can easily rotate. Yes. So these are special connections. So C is 2. So you must actually see them and solve them. So next time when you see this, you know the answer. Another special connection is when we mix them together. So we have this, and we have this one. Now, how problem solving skills? How do you approach this problem before you think about the solution? Because it's bunch of connections coming together. This is a pin, this is a pin, and this is special connection without name. To ease the solution, you just separate them in this way. This one is equal to so the pinky color one is here. I just separate them. It doesn't affect the, so I can say it's equal. They are equal. Now it is easy for you. You can say, okay, this one is a pin connection. The number of elements is 2, pinky color and white color. So C here is n minus 1, which is 2 minus 1, which is 1. Do you agree? It's a pin connection. The one that we just discussed. N minus 1. So C is 1. When it comes to yellow color, again, it's a pin connection. So N minus 1, 2 minus 1, 1. Just a simple pin connection. And then to that special connection, which doesn't have a name, it doesn't have a name. So you have to follow the method Okay, what about N? N is 0. Shear force is not 0. Moment is not 0. So C is 1. Right? So now you add them together. C is 1, C is 1, C is 1. So sigma C is 1 plus 1 plus 1, which is 3 for this connection. So this connection gives us 3 condition equations. Any question? Next one is what else? So we have a shear hinge. So in addition to the shear hinge, we have one element like this, another element like this. So you just need to separate them. So the equivalent structure is the green one, I just put it here. And then the red one, I just put it here. So of course for this one, C is n minus 1, which is 2 minus 1, which is 1. Oh. Minus 1, which is 1. For the red one is the same, n minus 1, 2 minus 1, which is 1. For the shear hinge, you must know, it's a shear hinge, so it's just 1. N is 0, moment is 0, shear force, N is not 0, moment is not 0, shear force is 0. So we already discussed this, so C is 1 for this. So we add them together. Sigma C is 1 plus 1 plus 1 is 3. So this special connection without a name gives us 3 condition equations. Now you are ready to solve an entire structure. So we can go through an entire structure, and then we can find C, R, etc. for this. We still have 4 minutes, so I use this 4 minutes to solve one more problem, and then we can go. This is the entire structure. Like this. It is A, B, C, D, E, F. This part sits on a pin support. There is a pin here. Pin support, roller support, roller support here. That's it. So we have to identify all of the parameters in this equation. Di is R plus 3K minus C plus 3. The question is asking to find degree of indeterminacy. So we start from one of them. For example, we start from support reaction. R is 2 here because this is a pin support. R is 1 here because this is a roller. R is 1 here. R is 2. I guess you all understand this because these are just roller and pin support. When it comes to roller, we have 1 reaction. When it comes to pin, we have 2 reactions. So we put them together, all of them together. How many number we have for R? 2 plus 2 plus 1 plus 1 is 6. So R is 6. Number of reaction is 6, which is part of unknown. Now, number of closed loop or ring This is one ring in pink, another ring in yellow, another closed loop in blue.
So that is a closed loop then?
Which one?
The triangle itself is a closed loop?
Yes,
I
because
wasn't sure. It was
yeah,
probably like the, okay.
it's a close because it's a closed loop. Right? There are three elements. Yeah, it's a closed loop. So
I thought maybe you'd label the other corners if that was the case.
no, if you move from one side to another side, you can just get back.
Oh, it's just a single.
It's
I
a
gotcha.
loop. Yeah.
Okay.
Yeah. So number of closed loop is 3. So K is 3. Number of condition equation. Number of condition equation. You help me here. See, this is pin. How many elements are connected? Be careful.
1.
If it is welded, yeah. So 1 minus 1 is 0. What about this?
1.
Yes, because it is also welded. So 1 minus 1 is 0. What about this? How many elements? No.
Wait, for rollers, wouldn't C be 1?
Yeah,
Is C would equal the number of elements?
It is not roller, it is pin.
Oh,
Well,
okay.
Yeah?
Okay.
It is not internal roller. It is,
Okay.
yeah. Yeah, I expect this kind of question.
Okay.
So what was another question? Yeah. So what about here? How many elements?
2.
Why you say this is 1 element, this is 2, this is 3?
But isn't that whole thing connected?
Yeah. So yeah, I should draw it in this way.
Okay.
Yeah. So it is not welded.
Okay.
So is 3 minus 1 is 2. And then here C
Looking
is
like the bottom corners.
C is 2 minus 1, which is 1. Here C is 2 minus 1, which is 1. Right?
Yep.
So you add them up together, C is how much? 0, 0, 2 plus 1 plus 1. So C is 4. So at the end, DI is 8. That's it. Enough for today.